Okay, all right. Yeah, so just I need one of you to monitor Piazza and the other to monitor Zoom. Okay, everybody, settle down. Get your name tags out. Please shut your laptops, all the usual good stuff. Just tell me your name. Emily. So when I stare at you like that, you just tell me your name.
It does not curve it like.
Thomas. I like the front benchers. They're the best students.
No, that's not a UI problem. That's like a much more foundational way.
I'm handling the technology.
Any questions from the last class? And how many of you actually got to view the lecture I did last night? 1, 2, 3, 5. So the majority of you didn't. I recommend that you do because we went over the basics of vector calculus, and that's something that you will need going forward, not just in this class. And the basic ideas that we explained are kind of useful. There's one little derivation that one little formula that I did not derive, which was the derivative of the loss with respect to the weights. If someone will remind me about it, then I'll make a post on Piazza on how it's obtained. Right? So let's begin. So here's where we ended in the last class. Or the classes so far, we've seen that neural networks are universal approximators. They can model any odd function, provided they have the right architecture. But in order for them to model any specific function that we're interested in, we must train them to do so, which means we must specify their architecture, and we must learn the weights and biases such that even with the appropriate architecture, the network is actually able to model the function that you're interested in. And networks are trained to minimize a total loss on a training set, which we do through empirical risk minimization. We use variance of gradient descent for this optimization problem, where the gradient of the error, which we call the loss, with respect to the network parameters was computed using back propagation. So here's how the whole thing was set up. We defined a loss function, which is the average of the divergence between the actual output of the network and the desired output of the network in response to any input. This is averaged over all inputs. This loss is a function of network parameters. So the gradient descent algorithm proceeded as shown. You initialized all network parameters, and then in each step, you went through each of the layers in the network, and you computed the derivative, the gradient of the loss with respect to network parameters, which was the average of the gradients of the divergences for the individual training instances with respect to those parameters. And this term was then used in the gradient descent update. You basically update the network parameters against the gradient. And of course, this highlighted yellow term, which is the gradient of the divergence for the individual training instances with respect to network parameters, was computed using backprop. So the overall neural network training algorithm looks something like so. You'd initialize all your weights and biases, and then you'd initialize all your gradients to 0, because before you process the data, you don't really know what these values are. And then you go through all of the training data, and you pass each training data instance through the network. This was the forward pass. And having done so, you now have all the intermediate values in the network. You can compute the divergence between the output and the desired output. And once you have that, you can perform the backward parse where you keep stepping back through the network and compute the gradient of the divergence with respect to the parameters of each layer. And having done that, then eventually you're going to compute the average gradient over the entire training set. And the gradient update takes a step against this average gradient. So this was the entire training process. And so the two steps were gradient descent on top, the computation of gradient on top, which was performed using backprop, and gradient descent used the outcome of backprop. Now, in today's class, I have only 4 poles, but because I wanted to have more than 4 poles, I became cunning. Pole number 0 is not counted, but you have to do it anyways. All right, 10 seconds, guys. This is an easy one. You don't see it on Piazza? What? Yeah, people are posting. It's called pole 1. Is it? All the poles are adjusted, okay? So this is pole 0. Obviously, my cheat didn't seem to work. But okay, let's close the poll. Can anybody tell me the answer here? Someone say it aloud. So what is the derivative of the with respect to the kth layer weights? A, which is the right one, right? So we saw this, the derivative of, in the vector format, we saw that the derivative of the divergence with respect to any weight matrix was the product of the input to the weight matrix and the derivative of the divergence with respect to the output of the weight matrix, right? The rest of them are wrong answers. Anyway, let's move on. So first question. We've looked gradient descent using backprop. Does this always give you the answer? So we're going to look at what are the conditions under which it gives you the answers and how we can actually modify this basic gradient descent approach to get a better shot of getting the correct answer. So first, is backprop always right? Now I'm using backprop as a proxy for gradient descent using gradients computed using backprop, okay? So for the longest time, people sort of conflated the two terms. And so you actually have papers which ask you, is backprop always right? So that's why that's where the term comes from. So does gradient descent find the correct solution even when it finds the global minimum? So remember, we are trying to minimize a loss function. And when you minimize the loss function, you're hoping that the minimum of the loss function will give you the correct answer, right? So let's go back here. Now, in this case, when I have a one-dimensional problem, we saw that over here, the correct answer is for the threshold to be out here. But for any given setting of the model, the threshold might be in some other place. You want to figure out which way to move the threshold to get closer to the answer. If you used a threshold activation, it wouldn't tell you. So we moved to a softer version of the threshold, which was continuous. And instead of simply counting errors, we counted the cumulative distance between the correct answer and the function that we were computing. And again, we said that if we minimize this cumulative distance, this is going to give you the function that minimizes the error. Is that always right? Can you give me a situation where the second mechanism can give you the wrong answer? Anyone? Adrita, can you? Does anybody want to take a guess? Lady there, can you shut the laptop? Please. When I ask you to shut your laptops, I really mean it. Okay? So can anybody give me the answer?
Is it possible to construct a specific data set where, like, for example, we have a red point that is like very far left and several blue point that is and by doing so we can like construct a case where minimizing the total distance to answer to actually like.
That's a good answer, right? But here's a very simple way of thinking about it. Suppose I had a very large number of red points out here. Then because you're computing the total distance for all the red points, although individually each of them is very close to the line, the curve never goes to 0, right? So each of them will try to push the curve out to minimize the gap. And just by having a very large number of red points over here, you can push the curve right past the first blue point and get a wrong answer, even though the correct answer exists. So this loss function that we are using, Lakshay, there's a question on your face. No, are you sure? Okay. So this proxy, the loss function that we are using, which is the cumulative distance from the target to the function, that's only a proxy to what you really want to minimize. What you want to minimize is the error, and minimizing the proxy, the loss, isn't guaranteed to minimize the error. This is something that you must keep in mind, right? So here is a more dramatic, so the point is in classification problems, the classification error is a non-differentiable function of the weights, and so our loss is a proxy for it. Minimizing the loss or the divergence may not minimize classification error. There's a very nice paper by Brady, Raghavan, and Sloney back in '89, which demonstrates this with very nice examples. So here is an example where you have a collection of red and blue training points. They're linearly separable. And let's assume that I'm just training one single perceptron. So that red line is going to classify separate the two classes perfectly, right? And now if you computed the total loss as we just defined it, and then minimize the total loss, it will find that decision boundary. Now, what was the other method we used? The other method was where we use a threshold activation and try to find the decision boundary. And what was the algorithm for that? What did we call that? Anybody remember? The perceptron learning rule, remember? So where you kept fixing for the latest one. And what was the guarantee that the perceptron learning rule had if the data were linearly separable? It would always find the answer, right? Now, in this problem setting, I add that one red point. The data are still linearly separable, right? The perceptron rule is going to find that boundary. But now assume that I have like 1 trillion of those red and blue points at those 3 clusters, and I just added this one little dot. And now I try to minimize the loss. Will minimizing the loss find this boundary? Why not?
Like shadowed by the millions of red points.
The cumulative evidence from all of the other points is going to prevent for any kind of, if you do not have bounds on the weight, you get some strange answers. But for any kind of restriction, even though the answer exists, you know that the dotted line will separate the two classes. Because this one little point is not overwhelming the evidence from all the rest of the data points, if you minimize the loss, you're probably going from that red dot to maybe from the dotted red line to the new red line, shift just a little bit, right? Now, if on the other hand, I move the spoiler, this extra point to the other place, the perceptron rule will find another boundary, which separates the two. But when you minimize the loss, the boundary is going to shift just a little. And so every time you move the spoiler, the solution found by the perceptron learning rule is going to swing around till it perfectly classifies the data, whereas minimizing the loss is missing an available answer. It's not that the answer doesn't exist. Yes, what's the question?
Is that though the global minima?
Pardon me?
Is that the global minima though? Like, is
It will be. So for any kind of restriction, unless you let the weights go to infinity, in which case the sigmoid becomes a threshold. For any restriction on the weights, that would be the global minimum. You would have a global minimum which does not separate the classes, right? And so, as you can see, you can just keep changing adding just one little spoiler, and you still have an answer which the perceptron rule will find, but minimizing the loss will not find it. And so the perceptron may change greatly by just adding a single training instance. Whereas when you minimize the loss, you might actually miss the available answer, but the solution is going to move just a little. Would you call this a bug or a feature? Why?
Because the model is very generalized with inductive bias.
So what, you're throwing a lot of jargon at me. Can somebody give me a better?
You're rejecting the outlier.
You're rejecting an outlier, right? If you have one data point which is completely away from this entire collection of data elsewhere, that one data point is very likely to be an outlier. So in jargon terms, the perceptron learning rule has no bias. It always finds the correct answer, but it has a high variance. The answer swings by changing just one point. Whereas minimizing the loss has a bias. It will often miss the answer, but it has low variance. It's not going to, you're not going to be able to make it swing by just adding one data point. Right? Yes?
In the differential activation that we looked at, we had argued that adding like a single point could make the sigmoid like differentiable activation structure that we used to like give us the wrong answer. Wasn't that also backpropagation?
So no, so different backpropagation is the mechanism for computing the derivative, right? And so we are saying that, and so if you replace the threshold by a differentiable activation and compute derivatives, compute the loss as we just defined it, compute derivatives and use gradient descent, you're right. That is the gradient backpropagation based gradient descent algorithm. And yes, that what we are saying is that can miss an available answer, something that the model can represent, because the manner in which we define the loss doesn't make that the global minimum. Right? Questions? Okay. So this was for a linear classifier. If you have a broader neural network, a deeper neural network with many neurons, it's actually going to model a nonlinear decision boundary. So you might have data of this kind, and the neural network may model that red curve, the decision boundary, which is shown by the red curve. Now, if you have a very large number of blue and red points, adding one more point, which is on the wrong side of the curve, is not going to make your network swing and completely change its boundary to fit that one point. And so the same concept extends even in the case of nonlinear decision boundaries. So backpropagation will often not find, what I mean by backpropagation is gradient descent using, where the gradients are computed using backpropagation, will often not find a separating solution, even though the solution is within the class of functions learnable by the network. So, got a question, Akshay? Yeah.
So I wanted to ask that if we are using the perceptron algorithm and the two binary variables are linearly separable, there might be infinite decision boundaries existing between them.
Correct.
So if we minimize the loss, will loss minimization find the perfect decision boundary that is the decision boundary's distance from the two binary variables?
No, so that's basically what we are saying over here. In this case, if you're minimizing the loss might give you that solid line, which is very far from the decision boundary. Yeah.
Is it possible that we add an additional penalty term for the misclassified points to affect the problem?
So the point is this, that again, within the class of solutions that you have over here, where you will find the global minimum is going to be not the answer. That is the point. You can penalize it, and you can make it, you can push it in different ways, and you can try to, for example, if I let the weights go to infinity over here, then it would actually find the correct answer. But that's not a way, that's, I know that even for finite weights, a correct answer exists. It won't find it. right? So the perceptron rule has low bias, makes no errors, but high variance, and backprop is as the reverse. And this extends even if your boundaries are nonlinear. Having one spoiler of this kind is not going to make the network change its mind completely. So this is, so backpropagation will not find a separating solution, even though the solution is within the class of functions learnable by the network, because the separate solution is not a feasible optimum. We're not saying that it cannot be implemented. It's not the optimum for your loss function. So one resulting benefit is that backprop trained neural network classifiers have lower variance than the optimal classifier for the training data. The optimal classifier for the training data is the one that actually separates the data. And the backprop trained model, and that can vary a lot depending on the training data. The backprop trained model is not going to vary quite as much. So here's a second poll. And this one's easy. I give you only 30 seconds. Okay, 5 seconds, guys. One, two, three, four, five. Okay. We can stop this. And does one of you people want to give me the answer? You folks at the back? Yes. Thank you. It is false, right? Isn't that strange? I say false, true. Okay, but yeah. Anyway, so far so good. Any doubts? Questions? No. So let's move on. The problem that we have is that we are defining a loss surface, and we are trying to find the weights that minimize this loss. We're defining a loss function, which is a function of the weights, and we're trying to minimize this loss. If you plotted the loss against the weights, it's going to be a surface of this kind. And so all of the assumptions, the little explanation that I made showed that you can have low variance or high variance depending on how you define the problem when you found the actual minimum of the loss. But then there isn't even a guarantee that you will actually find the true minimum of the loss. There are other things that can happen. So what does the loss function actually look like? There are all kinds of hypotheses about the loss function. Every couple of years, there's a new paper on the subject. So here are some popular hypotheses with some solid mathematical grounding, but each of them is defined for a very, very restrictive class of networks. So in large networks, saddle points. So what is a saddle point? A saddle point is a point where it's a minimum maybe in one direction, but a maximum in a different direction. So saddle points are far more common than local minima. And so if you have gradient descent, you could potentially get stuck in a saddle point. Another hypothesis is that you may not just have one global valley. You're going to have many small valleys. Each of them is what is called a local minimum. But then that all of these local minima are approximately equivalent, meaning if you compute the depth of all of these local minima is more or less the same. Now, this is for large networks. This is not true for small networks. And there are various other such hypotheses that solutions lie along a ridge. You can just fall into the ridge and so on. Now, what do these things look like? So before that, here is a quick summary of everything that we've seen. Neural nets can be trained via gradient descent that minimizes a loss function, and backprop can be used to derive the derivatives for the gradient descent. Gradient descent is not guaranteed to find a true solution even if it exists and if it lies within the capacity of the model to represent, because the optimum of the loss function may not be at this true solution. And for large networks, you can have the loss function itself can have a large number of these local minima and saddle points, which can confound gradient descent just to make things worse. So let's take a look at a little more on how this entire gradient descent, which sort of goes down this loss function and tries to arrive at the minimum. how does it actually behave? Now, in the discussion so far, we've assumed that if I perform gradient descent, I can keep taking steps, and eventually I'm going to arrive at some value, that I'm going to arrive, if not at a global minimum, at a local minimum, some place where the function's gradient is minimum or the function is, has got a value, right? So will it always do that? If I just perform gradient descent, is it always going to find a minimum? And if it does do so, how long will it take to get to the minimum? Now, it's hard to analyze for multi-layer perceptrons or neural networks in general because the loss function can be extremely hideous. So we will sort of look at it from the lens of functions that we know how to analyze. Convex optimization. This is called the spotlight, streetlight effect. All of you have heard this joke. Some guy loses his keys in a bar, and then he's found searching for them under a streetlight because, hey, you can't see anything in the bar anyway. You might as well look where you can. So we know how to analyze convex functions. We will do that. And then we'll try to generalize to more complex functions. Now, what is a convex function? Does anybody know? What's a convex function?
Opening upwards.
Opening upwards. Is that enough? Yes.
If we take any 2 points in the function and try to join them with a line, value of the function is always u1.
If I take any 2 points on the function and connect them up, then the function is always going to be on or below the line, right? So here, for example, I have this function here and this function here. Both of these, if I take any 2 points and I just draw a line between the two, the actual function is going to lie underneath. Same thing over here. So that we can define convex sets in the same way. If I take any 2 points in the set and draw a line, every point on the line is going to be within the set. So these two are convex sets. Now this is not a convex function. This is still a bowl, but it's not a convex function because if I take a point here or a point here or any 2 points above it and draw a line, that line is actually intersecting the curve. So this one is not convex. And for the same reason, this is not a convex set. If I draw a line between these 2 points, it falls outside the set. So we're going to look at the class of functions and solution sets shown in the upper figure. So we are speaking of gradient descent and convergence. What do we mean by convergence? The idea of gradient descent is that you started off at some initial estimate, and then you found the derivatives, and then you kept taking steps in the direction of the derivatives. If you keep doing that, you want the answer, you want the updates to eventually arrive at the solution. So here, for example, as it's a representation of the level sets of a function. The minimum is in the darkest region. And you want gradient descent to sort of take steps and slowly arrive nicely and smoothly at the minimum. That would be called converging. On the other hand, you can have behavior of this kind, where it comes here and it keeps bouncing around because every time you take a step in the direction of the gradient, you just step clean across the solution, and then you have to keep moving around. So that's jittering. And then things can get worse. Instead of converging to the solution, if you just follow the gradient descent rules, you may end up taking larger and larger steps and actually diverge. So what are the conditions for the function to the algorithm to actually converge? For that, we're going to look at convex functions, and specifically we'll look at quadratics because in some sense quadratics are the nicest convex function. They have a nice clean bowl-shaped structure which never really flattens. If you have a cubic, it begins flattening near the minimum or any higher order. And if you have some order which is less than a quadratic, then it's not steep enough. So it's a sweet spot. And a quadratic function has a formula like the one given on the top left. I have the half there just for convenience, but a quadratic function is a function of the second power of the variable, right? So if the variable is scalar, then the quadratic function is going to be, e equals half of a times w squared plus some b times w plus c. Now, if I want to find where the place where this function is a minimum, how would I do it? If I take the derivative and equate it to 0 first, is that going to be a minimum or a maximum? So what is the condition on this for there to be a minimum and not a maximum?
the second derivative should be greater than.
The second derivative should be greater than 0. So what is the second derivative here?
It is B. A.
The second derivative is a, right? So if the constant that multiplies the quadratic term is positive, it's an upward bowl and it's going to have a minimum, right? And what is the location of the minimum? We all know this, minus b plus or minus square root of b square minus 4ac over 2a, right? So, but then if I want to use gradient descent, instead of simply solving for the minimum, here's what I can do. I can use the standard gradient descent rule. I can say I start off with some initial estimate, and then I take a step against the derivative. So it's going to be w minus eta times dE over dw computed at the current point, right? So what is, if I want to use gradient descent, then what is the step size eta that I must take to arrive at the minimum fastest? Can anybody take a guess? So let's see how that's derived, right? How many of you are familiar with Taylor expansions? Taylor series. You've heard the term, it kind of rings a bell, right? So, okay. Is there anybody here for whom that bell is particularly loud? Someone who's courageous, raise your arm, raise your hand. I want you to explain, okay, Laksha, explain Taylor's. You don't remember. Okay, so here's what we said, right? Suppose I have a function, then, and this is some f of x. I want to define some f hat of x such that f of x and f hat of x are the same, are the same at some point x0. Then if I say f hat of x equals x0, are these two functions the same at x0? Yes or no? Right? So I'm just calling this, no, sorry, f of x0. Right? So are these two functions the same at x0?
Yeah.
Okay. How do I make the second function such that the derivative of the function is also the same at x0? Yes, I want the second function f hat to be such that not only is the f hat the same as f at x0, I want the first derivative of f hat to also be the same as f at x0. So here is what I can do, right? I can just say plus f prime of x0 times x minus x0. You can check. If I take the derivative at any other point, we can't really say, you can't really say anything, but at x0, what is the derivative? First, check that this function equals f of x at x0, because x minus x0 cancels out this term at x0, right? But if I take the derivative, this goes away, this term goes away, only f prime of x0 remains, right? And so now these two have the same value and the same first derivative at x0, right? What if I also wanted to have the same second derivative at x0? What would I do? I can just say plus half of f double prime of x0 times x minus x0 squared, right? And if you take a look at this, then because of x minus x0, this is the only term that remains when I'm computing the function itself. So f hat and f are the same at x0. If I take the first derivative, this guy will go away. The second term is going to have an x minus x0 remaining. So both of them will disappear. All you're going to be left with is f prime of x0. And so the first derivative is going to be the same for both. If I take the second derivative, then this disappears. This is just a linear term. This disappears. F double prime of x0 is the only one that remains, right? So I can keep adding this. I can say 1 over 3 factorial f triple prime of x0, x minus x0 cubed, and so on. And if I make all infinite derivatives of f hat and f match, then the two functions are the same, right? Otherwise, it's an approximation where the first few derivatives are identical, right? So that's your Taylor series expansion, okay? You guys understand this? Does this ring a bell? Right? So what is the Taylor series expansion of a quadratic function at any point? I have half of ax squared plus bx plus c, and this is my f of x, right? And I want my f hat of x computed around some x0. So what is the Taylor series expansion going to be? This is going to be f of x0, right? Plus, what is the first term?
Ax plus b into x minus x naught.
So it's a x0 plus b times x minus x naught, right? Plus,
A by 2
I can just write this as f prime at x0 times x minus x naught, right? Plus, what is the second derivative? A, right? F double prime of x naught times x minus x naught whole squared. There's a half, and this is going to be A, right? Do I need to add additional terms?
all of them will be 0.
Because all these additional terms are 0. So now the two are identical, right? That Taylor series expansion is identical. So now if I write this out, I can just write this as so now if I write this in this manner and I minimize this with respect to x, what is the solution I'm going to get if I minimize the second term with respect to x? I take the derivative and equate it to 0, right? If I take the derivative, you're going to get f prime of x0, because that's the this one has no derivative. This one just gives me f prime of 0, and this is going to give me, why do I keep dropping the chalk? Plus f double prime of x0 times x minus x0 equals 0. If I take the derivative and equate it to 0, right? So what is x? So if I say this, then I can say f prime of x0 minus equals f double prime of x0 times x minus x0, right? I can write this down here, right? And then I can move x0 to the left, and this is x. That's the solution, correct? That's a single solution that I've obtained using the Taylor series expansion. If I write that, basically, if I start off at any estimate, then a W min over here is going to be the second inverse of the second W, the current estimate, minus the inverse of the second derivative times the derivative, right? That's the global minimum. Single step equation. I mean, does everybody see where I got the equation from, right? Now compare this one to the solution here. What must the optimal step size be to get to the solution in a single step?
1.
What is eta?
1.
Compare this. How is eta equal 1? This term is the derivative, right? So eta has to be the inverse of the second derivative. That makes sense? Right? So if from any point you use a gradient descent rule where your step size is the inverse of the second derivative, you're going to get to the solution in how many steps? What was the question? There's something on Zoom. Okay. So what would happen? Simona, is that making sense? She looks puzzled. Okay, so where did I lose you?
So in the part where you calculated x naught equals the first derivative.
I didn't calculate x naught, I calculated x. I took the Taylor series expansion around x naught, and I said, what is the x where the function is minimum.
Is minimum when x is f.
So this is, if I take the derivative and equate it to 0, then this is the equation we got, which gives me x equals x naught minus f prime of x divided by f double prime of x naught, right? So this is the solution we got, right? Which is like saying the eta equals f double 1 over f double prime of x naught. So is that clear to everybody? Yes, yeah.
Isn't the Taylor series expansion equal to the function only at x naught? How do we know they share the same minimum?
If they share all, so if the Taylor's theorem, right? If you match all infinite derivatives at any point, then the two functions are identical everywhere. Right? Here there are only two derivatives, we match them, yes.
This value of eta, would that be only for a quadratic function?
This is true for quadratics at this point, right? And that eta is, yes, Manu.
If you don't have the actual e function, how do you calculate it?
Let's assume that we have it. Don't ask me too complicated questions, right? Okay. So the optimal step size is the inverse of the constant for the quadratic term, right? What would happen? I'm taking too long, but how did I lose my chalk? There was a chalk somewhere. Okay, several chalks. So now I know that if I start off from some W0, and I say I take W0 minus f prime at W0 times 1 over f double prime at W0, right? So this means that if I start off from this is W, this is the function E. If I start off from some W0, in a single step, I'm going to end up at the minimum, right? What if my step size is greater than this? What would happen if the step size is greater than this?
I will diverge.
Will it diverge? It's going to overshoot, right? If the step size is greater than this, it's going to go here. If the step size is lesser than it, so if the step size is lesser than the optimal step size, it's going to do something like this, right? If the step size is greater, it's going to overshoot the minimum. It's going to go to the other side of the bowl. But then at the next iteration, it's going to do this, and this, and this, and it's going to come here, right? What is the step size at which it will never come to the minimum? If it's twice the optimal step size. If it's twice the optimal step size, it's going to go straight across to the other side and keep bouncing back and forth. If it's more than twice the optimal step size, it's going to walk out of the bowl. That makes sense to everybody? Yes, Giovanni?
Regarding a previous point, we said that the solution where all the points are correctly separated, it's not the optimal for our loss.
Yeah.
Is it that because we might get stuck in a local minimum, or?
No, that's a global minimum.
Okay.
In that case. So again, we also show, I explained why that would be the case, for instance, with the one-dimensional case, right? So anyway, so you see what's happening. Yeah.
How do we derive that twice the amount of twice of A will make it diverge?
Because this distance is going to be, it's a symmetric function. This distance is the same as this function distance, right? Twice the step size is going to get you back at the same height on the other side. So, and then anything more is going to take you up. Okay. And so here is the property you have. The optimal step size will take you to the minimum. If you're lesser than the optimal step size, you're going to carefully walk out to the minimum. If you're greater, you're going to jiggle back and forth, but you'll get to the minimum. If you're too far, the step size is too great, it's more than twice the optimum, you're going to equal to or more than twice the optimum, you're going to diverge. Okay. This is for a function of a quadratic. What if you don't have a quadratic function? If you have a generic loss function. For a generic loss function, here's a standard technique that we will use. You can just, at the current estimate, you can take a second order Taylor series approximation and then find the minimum of the Taylor series approximation. And then again, that won't be necessarily the minimum because you have an approximation. Repeat the process, right? But even here, if at any point your step size is greater than twice the second derivative in twice the inverse of the second derivative, then you can diverge, right? So that's for univariate functions, where I showed you a function of a single variable. What about multivariate functions? What if x is a vector? If x is a vector, then this is what the function is going to look like. The quadratic still has the same property. It's going to be, except now it's going to be in terms of same format. It's going to be in terms of matrices and vectors. So W is a vector, and so the quadratic is half of W transpose AW plus some, W transpose B plus C. It's still a quadratic. But then to understand it, let's take a case where you have two variables, right? And I'll just call them x1 and x2. So then I can write my quadratic as x1 squared half a1 x1 squared plus b1 x1 plus c1. Well, I can just leave a constant c plus half a2 x2 squared plus b2 x2, and the c is constant, right? This is a quadratic in two variables, correct? You agree? So I can write this as a function. I can plot this as a function of two variables. The x-axis is x1, the vertical axis is x2, the horizontal axis is x1, and the function itself, I'm showing you the level sets, and these are going to be bolts, right? So this is a simple case where I have a quadratic function of two variables. So this is an instance, this is just like the formula on top, except that I'm assuming that the matrix A is diagonal. If the matrix A is not diagonal, it's like taking this entire page and rotating it by a small angle. That's it. So you can still work. It still makes sense to just think about the diagonal A, which is like saying I have the sum of quadratics of two different variables. If I plot it, it's going to look like this, right? Now, observe that if I'm trying to find the minimum of this function, I'm trying to find the minimum of both functions, right? Simultaneously find the minimum of both quadratics. And here's what it's going to look like. If I take many vertical slices, so if I take vertical slices, if I take slices at different values of x2, this guy is not a function of x1, right? So this is going to be the minimum of the first component is going to be the same regardless of x2. So which means that if I take slices of this function at different values of x2, I'm just going to get the same bowl at different heights. The different heights occur because this term is going to be different for, the second term is going to be different for different x2s, right? But the value of x1, where all of these bowls are going to have a minimum, is always going to be the same. That makes sense, right? So also if I took horizontal slices, the value of x2, where the slices are going to have a minimum, is always going to be the same, right? And it's always the same quadratic. Okay. So now, if I take the bowls with respect to x1, the bowls with respect to x1 have this guy as my constant, right? For the quadratic term. What is the optimal step size for x1? Is 1 over a1, right? What is the optimal step size for x2? It's going to be 1 over a2. You guys with me, right? The two are not the same. That causes a problem. To see why, remember that when I actually use gradient descent actually uses this rule. W equals W minus eta times the gradient, right? Which means that W1 equals W1 minus eta times dE over dW1. W2 equals W2 minus eta times dE over dW2. So the step size is always the same for every component. Do you see a problem arising from this? Can anyone visualize that this is going to be a problem?
So one of them might be greater than twice the other.
Thank you. Beautiful, right? So skip this. Here's what can happen, right? I have this case where I have the function of two quadratics. It's a quadratic of two variables. And you can see that these are ellipses. The two variables have different eccentricities, right? The first one, the optimal step size for the first component, x1 is 1 in my example. The optimal step size for x2 is 0.33 in my example, okay? So now if I have a step size which is greater than 2 times 0.33. So let's say I have a step size of 0.67, right, which is greater than twice 0.33. Is it still good for x1?
Yes.
Right? For x1, it is still good, but for x2, it is bad, right? So what will happen is that this guy is going to, in x1, it slowly comes and arrives at the minimum, but for x2, it diverges, right? On the other hand, if I have a step size which is exactly equal to 0.66, what would happen? For x1, it still arrives at the minimum. For x2, it just keeps bouncing around, right? Over here. Suppose I have a step size which is exactly equal to 1.5 times the 0.33. Then what would happen? So if it's 1.5 times 0.33, it's going to, wait. So that's this guy, right? It's going to sort of converge monotonically along x1, but it's going to converge with oscillation along x2. If I have the step size which is exactly equal to 0.33, right? So it's going to get to the optimum for x2 in a single step, but it's going to arrive slowly at the optimum for x1. And if the step size is less than 0.33, it's going to arrive slowly at the optimum along both directions. Now, what do we want? We want the algorithm to converge as fast as possible, right? So you want the step size to be the optimum for every single component, but then the components have different optimal step sizes. And so if you try to make it this optimum for the smallest optimal step size, it might be too slow for the others. It will never, it's going to take a long time to converge. On the other hand, if you try to make it optimal for the one with the largest step size, it may just end up diverging. And so the real challenge is going to be this. How do we actually make this behave when the different dimensions can all have very different behaviors? Now, this is for quadratics, right? But if I take it for, if I use non-quadratics, I mean, I'm not following my slides. I'm hoping that the story is coming across. If I have non-quadratic functions, like functions like this is a convex function, but it's definitely not quadratic, then the standard approach to solving these is to take a second order Taylor series approximation at the current estimate, which will give you a goal. And then you want to get to the minimum in a single step, right? And then at that point, you can create another bowl and keep repeating the process. But then even here, you're going to have the same problem. The eccentricities on along the different directions may be very different. And so what is the optimal step size in one direction can be completely off for the other. It can make it diverge for the other, or it can make it extremely slow on the other direction. So here is the real constraint is going to be the ratio of the largest optimal step size and the smallest optimal step size. If this ratio is very large, you have problems. Because if you're following the smallest optimal step size, it's never going to converge for the other directions. It's going to be very slow, right? On the other hand, if you try to follow the larger optimal step sizes, it's going to diverge for the other directions. So, questions? Any questions? Yeah.
This would work only if like each of the directional components are also convex, right? Like they have to be specifically.
So the explanation is for convex. When things are not convex, it gets worse, right? And so even there, if you look at it locally, the same kind of character behavior follows, yes.
Can we use feature scaling to mitigate this?
Good question. Look at the slides. Yes.
Related to the implementation of the network, so like as we read before, for larger networks, the network might become more saddle points, right? So is there some relation with the depth of the network to like how
No, the loss function is a generic function. You can make no predictions about it. So to answer, was that Lakshay who asked about scaling? So the way you would scale it is to multiply scale the space using the inverse Hessian. The Hessian is a matrix of second derivatives. It's explained in the slides. And you're not going to be, for something like a neural network with 1 billion parameters, the Hessian is 1 billion squared. You're not computing the Hessian anytime. You're not going to be doing that, okay? So the problem is this, that what is an optimal step size for one direction may not be the optimal step size for the other, and this can cause problems. But then all of this analysis based on trying to ensure that the network, the gradient descent does not diverge, right? We wanted it to converge. Is convergence even important? Do you always want it to converge? Yes or no? How many of you think yes? Raise your hands. And how many of you think no? Raise your hands. And how many of you express no opinion? Raise your hands. That's iterative, right? Okay, let's try this again. I want everybody to have an opinion. How many of you think yes? Okay, you always wanted to converge? And that seems to be the majority opinion. That's not always true. It's a trick question, clearly, if I'm asking it. Let's say you have a loss function of this kind. And if your initial estimate is in that small bowl, you do not want it to converge because it's going to go into the local minimum, the nearest minimum, which is a horrible place to be. You want it to go to the global minimum, which means you want it to escape the well, right? So in this case, what is your solution? Obviously, you want it to converge eventually, but you don't want it to converge immediately. So what would you do? Pardon me? A scheduler. Beautiful, right? So what you would do is you want to start off with a large learning rate so that you have a good chance of escaping any local minima, and then slowly decrease your learning rate, the step sizes. And so if you do that, then you expect that eventually, as you do this, you're going to end up in a large bowl where your step size is small enough that it's smaller than the width of the bowl and you'll find the minimum. And the assumption over here is that large bowls are more likely to be good minima than small bowls. It still doesn't mean that it's a global minimum, but then there's an expectation that it's a better minimum. So start with a large learning rate greater than twice the optimal step size. If you normalize it greater than 2, and then gradually reduce it with iterations. This is what you really want to be doing. So how do you decrease it? You've seen some of these schedulers in your homework. So there are various decay schedules like eta k. You start off with some initial step size, learning rate eta 0, and then at the kth step, there's just going to be eta 0 divided by k plus 1. So it keeps decreasing. Or you can, that's linear because it's decreasing linearly with iterations. It can be quadratic, so divided by k plus 1 squared. Or it can be exponential. There are different ways of doing it, and there are various techniques like try to do something on held out data. If it's not a neural network with smaller problems, you can try to optimize the learning rate on held out data. But there's a logic to all of this. And this logic we will cover in a couple of classes because this becomes more appropriate when we begin talking about stochastic gradient descent. So gradient descent can miss obvious answers, but this may be a good thing. And convergence issues abound. The loss function surface has many saddle points, although perhaps not as so many bad local minima. Gradient descent can stagnate on saddle points. Vanilla gradient descent may not converge or may converge too slowly. And this is because the optimal learning rate for one component is not necessarily the optimal learning rate for the other components. So I've given you all the hints necessary. What is the solution? Different learning rates for different components. That would be the obvious solution, right? But then what problems do you expect when you want to just do this? Have different learning rates for different components. Calculating second order derivatives is not possible. You don't know. You do know that each component needs a different learning rate. You have no idea what this learning rate must be. And so trying to determine so many learning rate parameters is going to be quite impossible. You know, if you begin looking at trillions of parameters like the latest neural networks, obviously that's not something in the realm of feasibility. So here's a poll. I got chalk on your hand. This is a simple one, so I'm only giving you 30 seconds also because I'm running out of time. Yes. In a quadratic setting. Okay, first, time's up, guys. What's the answer? Okay, thank you. Right? Yes, what is the question again?
So when we get to more complex problems such as neural networks, we can't really calculate the optimal learning rate because it's not quadratic anymore, right? And
So you can, so again, you can take a quadratic approximation and try to find the optimal learning rate. So, and, but yes, you have a valid point, right? So there was a question there, yes. Yeah.
So where the global minima will depend on the function, right? So
Yes.
when we make a generic, when we do the generic weight schedule, decay schedule, when we use a generic decay scheduler, how will that fit to like different functions?
You're asking a very deep and profound question, honestly. So it turns out that we have really, there's only one, there are very few solutions which guarantee that you will actually find the optimal the global minimum, and they are based on stochastic methods like annealing, which will take forever. So we just sort of try to find the best minimum we can, and we live with it. If the minimum has a small enough loss, we kind of hope that it works. Yes?
Professor, I didn't understand what you meant when you said that we don't always want to converge the gradient.
So that's over here, right? Yeah. So look at that. If I had the optimal step size at the very beginning, where would it converge?
Okay, but don't we want it to converge at the global minimum at least?
You do, but the point is, there's where you want to go and there's where you don't want to go, right? We really don't know where you want to go, but you can be much more certain about where you don't want to go.
Okay.
And so that's why, yeah. Yes, Chetan?
You said for more complicated loss functions, you can just take a quadratic approximation. What if that is not a good approximation?
We don't actually do it because if you're a neural network, finding quadratic approximations is quite impossible because computing the second derivative is itself going to be too expensive. So we don't even go there actually. Yes?
So this relies on the assumption that the larger the bowl, the more likely you end up in a global minimum.
Yeah.
Is that usually the case?
Yeah, these are just assumptions, right here.
Is it usually preferable to only have decaying learning rates, or can we also have something like an oscillating learning rate so that it increases later as well if needed?
Eventually, when you begin approaching the minimum, you really don't want your learning rate to increase. You will be you will overshoot. So you can have all kinds of strange erratic behavior at the beginning, but eventually it does have to converge. Yeah.
So what if we already start at the horizontal point to the global minimum? Like, is there a way we can like estimate the possibility? Like,
you really can't. But then, if you follow the appropriate scheduling, if you start off in a big bowl, then even if you go out, you'll eventually come back into the bowl.
Okay.
Right? Because the bowl is deep. If the bowl is deep, eventually you're going to go back. And even if you climb up, you're going to go back down. That is the assumption behind this. Yeah.
You mentioned that if we start with the appropriate scheduler, at the start we do not even know what exactly the function is. So isn't it then how will we know which is the appropriate?
You don't. There's a lot of heuristics, right? You will do this in your homeworks. Let me continue. Okay. This one, the step sizes that are greater than twice the inverse of the second derivative can cause it to diverge. So many of the divergence causing learning rates may not be a bad thing, particularly for ugly loss functions, decaying learning rates provide good compromises between a good compromise between escaping poor local minima and convergence. Many of these issues arise because we force the same learning rate on all the parameters. So let's take a step back. The problems arise because of requiring a fixed step size across all dimensions, because the step sizes are tied, right? And let's try releasing this requirement. But then we have to deal with figuring out what is the optimal step size for each component. Let's work out some heuristics. The simplest techniques that were originally proposed were things like rprop and quickprop, which just looked at local functions for each parameter. And now the point is this. The parameters are coupled. If I go towards the minimum for one parameter, you may actually end up going the wrong way for the other parameter because these things are coupled. But you still sort of work locally on each parameter. And let's look at rprop. I won't go over quickprop, but quickprop works better than rprop. Here's what rprop was called resilient propagation. It's a simple algorithm followed independently for each component. And so the steps in different directions are not coupled. At each time, it doesn't even look at the value of the derivative. It just looks at the sign. It says that if I'm going in the correct direction, let me increase the step size. That's it, right? If I'm going the wrong way, let me decrease the step size. How do you know that you're going the correct way? How would you know that you're going the correct way? Value, that's not enough, right? So you could still have overshot your minimum. Then if you continue in the same direction, you're going to go the wrong way. You want to look at the derivative, right? If the function is decreasing here, and then I take a step, and the function is still decreasing, I'm going the right way, right? If the function is decreasing, I take a step, and I'm at a lower loss, but now the function is increasing, the minimum is behind me. Simple logic, right? So that's rprop literally just uses this very trivial logic. Here's what you do. You start at some initial location and compute the derivative. You have some initial step size. Then so the derivative, the brown arrow shows the sign of the derivative. Here it's negative, which means you want to go forward, right? So then you take a step and you get to the new solution. Then when you get to the new solution, you check the sign of the derivative. The sign of the derivative has not changed. You're going the right way. So you increase your step size by some factor alpha. And then you check the derivative again, and the derivative is still, if the sign has still not changed, you're still going the right way, you increase your step size further by multiplying the previous step size with alpha. So alpha is a factor that's greater than 1. But then eventually you're going to arrive at a situation like this, where you took a step, and your step took you beyond the minimum. And so now if you inspect the derivative, the sign of the derivative would have changed. If the sign of the derivative has changed, then what would you do? You go back to the previous place and take a smaller step, right? So whatever the step was, you go back there and then multiply the step size by some factor beta, which is less than 1, and repeat the process. And eventually you're going to arrive at the minimum, right? Very simple algorithm. There are a lot of slides explaining this. So there, the derivative has changed sign. So you go back to where you were, and now you take a smaller step, right? And it's a trivial algorithm. If I asked you to come up with it, based on this explanation, you'd probably come up with it yourself, right? So easy. So this one, it turns out, is actually a very effective algorithm. Even now, this is a fantastic algorithm which outperforms many of the state-of-art techniques for optimization. And I'm always surprised that it's not more popular. You can still find it in PyTorch, but rprop, it's conceptually trivial, and it's beautiful. And here's the thing. You're only looking at the sign of the derivative. You're not actually looking at the derivative itself, right? The values. So I have some pseudocode for it. I'll skip the pseudocode. The concept was important. You usually have some additional heuristics. You don't let the step become too large. So there's a cap on how large the step can be. You can keep increasing the step size. And then eventually, if it gets large enough, you cap it. Similarly, when you shrink step sizes, you go there, you find your overshot, so you come back. Yeah.
Professor, in the previous slide, does that graph, is that convex?
That's not convex.
Okay.
It's definitely not convex.
But then, let's say you were to apply the same with multiple minima. Does rprop work there as well?
So again, it's going to find you a good minimum. There are no guarantees about finding the best minimum, right? So yeah.
But we said that like this process is only for a single dimension.
You would do this independently for each dimension. All you need to know is maintain the current step size and the current derivative, right? So you don't need to store a lot of information. Yeah, so again, you will still need backprop to compute the derivative so that you can find the sign of the derivative. So backprop, yes.
So then would alpha be different respect to each of the weights?
No, so the alphas, you just have two parameters, alpha and beta, that's it, right? The step sizes are going to be different for each of the weights. You start out with some initial step size, and you keep scaling it up by alpha, and then if it overshoots, you pull it back by, and scale it down by beta, right? That's it.
So the step sizes would be different for each.
Yeah, with the alphas and betas universally. Yeah.
You said you'd put a cap on it. Why?
Because if this is just a heuristic, if because the step size can just keep going off and become really large, and that's it, and it'll blow up. Same thing. You don't let it shrink too much. At some point, you just go across and reset. Yeah.
Is the intuition for increasing the step size that hopefully, like if we cross into the next bowl, then that's likely?
The intuition is that if I'm going the right way, then I'm more confident and so I can take a larger step size. So the more confident you get, the larger the step size it is. That's it, right? It's not about jumping into the next bowl. It's just about the confidence that you're going the right way. Yes.
If we don't cap it, won't we get to the minima faster?
In practice, you should try. You won't. You will get to the minima properly sometimes, but then eventually when you overshoot, you're going to overshoot by so much that you're going to have problems coming back.
When the gradient sign actually changes, is it necessary to go back one step?
There you can do it in different ways. So you could start off at the new location, and you could start off with the new location and change this, change the sign of the.
Because the sign is anyway opposite, so it's going to go to the opposite direction anyway in the next step. Right?
So if you go back, and what happens? You're resetting it, right? So you can reset it and start from there again, or you can go back and take a smaller step. These are different heuristics.
Just to confirm, so this algorithm has a higher probability of getting stuck in local minima and not converging out like this.
No, so this will actually get you to global minima. I mean, it'll get you to minima. All of them have the same problems with local minima, right? And in fact, because of the manner in which this operates, there are situations where this is more likely to give you a global minimum because the steps get large. And so eventually the only places where that large step size will sustain is in big bowls. Yeah. All right, let me continue, right? It's a remarkably simple first order algorithm that is frequently much more efficient than gradient descent, can be competitive against some of the more advanced second order methods that are around today, and makes only minimal assumptions about the loss function. No assumption of convexity, nothing. All you're looking at is the signs of the derivatives, right? Now, there's another poll. I'm not going to be able to complete, but I'll skip. But those were skippable. Okay, let's stop because I'm running out of time. What's the answer? A, right? R prop will revert to the earlier estimate. If you overshot, it's going to revert to the earlier estimate and take a smaller step, okay? Easy one. So there are other solutions of the same kind. Quick prop was invented by our own Scott Fallman. It's even more efficient than R prop, where it turns out that instead of trying to compute the second derivative explicitly, it looks at the updates, the derivatives at consecutive updates, and use that to come up with an approximate estimate of the second derivative. It's one of the fastest training algorithms still for many problems, right? But anyways, going back, So second order methods, which we didn't actually talk about, can normalize the variation across dimensions but are complex. We can adaptive or decaying learning rates can improve convergence. Methods that decouple the dimensions can improve convergence, right? But we still have this problem that we don't know what the optimal step size is in any particular direction. So we're coming up with heuristics. So let's take a closer look at the solution itself, at the problem, and see how things can be adapted. So if you have dimension independent learning rates, the solution will converge in some directions and diverge in other directions, right? So what happens? What happens when something diverges? It's going to oscillate back and forth, correct? Whereas if it's converging, it's going to keep, the steps are going to keep shrinking. So let's keep track of the step sizes. How big was the step in this particular direction? And if you keep track of that, if the steps keep getting larger and larger, then you're probably diverging in that direction. If they keep getting smaller and smaller, you're probably converging in that direction, right? So just by keeping track of this behavior, you can take a guess as to what the step size must be. So based on this simple principle, you have these so-called momentum methods. And what momentum methods do is that they maintain a running average of all past steps. In directions in which the convergence is smooth, you want the steps to, you want to sort of increase the step size. In directions in which you're seeing a lot of oscillation, you want to decrease the step size, right? So over here, for example, in the first one, in the vertical direction, the steps are good. Maybe you even want to increase the step size. But in the horizontal direction, the step size is not good because it's oscillating. You want to decrease the step size, right? So what would happen if you maintain a running average? If you maintain a running average over here in the vertical direction, the running average is always going to point downwards, right? What about the running average in the horizontal direction? The positive oscillation will cancel out the negative oscillations, right? As you keep bouncing back and forth. And so if, instead of simply using the latest derivative, if you use the average of all past derivatives, you expect such behavior to get normalized out, right? And so that gives us our momentum methods. You maintain a running average, and this will sort of enhance the steps in directions where the convergence is smooth and shrink them in directions in which you have oscillations. And so here is the simple mechanism for this. So at each point, you're computing the current derivative, but the step size is going to be some beta times the previous step size minus some eta times the current derivative. So the minus is because you're always walking against the derivative, right? So you're saying that the current step size, step that you're going to take, is actually obtained as a running average of derivatives across all iterations. And the running average is simply like saying, xk equals xk minus 1 plus the new term, right? So here, wk, delta wk equals some beta times delta wk minus 1 minus whatever step you would recommend based on the latest derivative. And so you compute this running average, and the actual update is performed using the running average. Is this making sense? Right? It's an easy method. So if you look at what happens when you use the simple algorithm over here, you'll find that if you're just doing gradient descent, these are the directions of the derivatives at each point. It's going up and down, right? Whereas if you're using a running average, the vertical oscillations get canceled out. The horizontal steps sort of stretch out a bit because the running average supports itself. And so it sort of converges. The vertical oscillations are decreased. The horizontal steps get to the solution faster. And so you're going to get to the solution much faster. Yeah.
Oh, I think, figured my question out by looking at the notation more clearly.
Okay.
Yeah.
All right. So I just have pseudocode for this. This is the classic momentum method, where at each step you compute the derivative, and then, so this was standard gradient descent. Wait, this is the momentum method. You compute the derivative, and then the actual step size is computed as a running average of the derivatives, beta times the current step minus eta times the new gradient. And you have beta and eta are heuristically set. Typically, beta is 0.9 and eta is whatever learning rate you choose. And then the actual update is done with this running average step size. You do this until loss is converged. Now, there's an upgrade on this method. This is the standard momentum method. But here's how the momentum method, I'm going to go 2 minutes over, so just bear with me. At any iteration, you're computing the current step, right? So let's say at this iteration, this was the step taken, right? Then over here, you're computing the current gradient, or the gradient would be outwards, so the step according to the current gradient. And the actual step size is going to be a running sum average of this guy and this term, right? And so it's going to be this blue line plus a shrunk version of the red line, and so that's going to be the actual step. So what you're doing is you're computing the gradient now and adding the current gradient to the previous step to determine the actual step that you will take. So this is the momentum method, right? This is slightly suboptimal. It turns out that if you take the gradient now and then average it with the previous step, you can end up in a place where the gradient is actually not necessarily what you expect it to be. So a better thing to do is to say, I'm going to go there and then take a step against the gradient, as opposed to say, I'm going to take a step against the gradient and then add in the previous step. And so if you change the order, so there are 2 steps over here, right? First, you take a step against the gradient of the current location. Then we add a scaled version of the previous step. So this was how the momentum method was done. If I reverse the order, I first take a step, which is a scaled version of the previous step, and then take a step against the gradient. It turns out this actually ends up being even more optimal. So this is Nestorov's accelerated gradient method. And so here's what the formula is. The current step size, so what you're doing is you take a step, which is a scaled version of the previous step, and compute a gradient at the new location. And that gradient is what you're adding to the previous step size. And that's going to be an updated new step. So if you compare this with standard momentum, this is an example from Hinton, you can see how the Nestorov's method converges faster. So if you were using standard momentum, you'd come here, you'd compute the gradient, and then you'd add a scaled version of the previous step and end up at this point. Whereas if you're using Nestorov's method, you just extend it first and then go against the gradient, and that's going to end up at this location. So you can see how Nestorov's method gets there even faster than momentum does. But both of these techniques, so we're going to return to these trend methods again very soon, but both of these techniques are based on a very simple principle that if you use some kind of a running average, then oscillations will get canceled out, and you're going to effectively end up with a different step size in each direction. Because in some directions, the step sizes are, except the way you're ending up with a different step size, and you're ending up with a different step in each direction as opposed to a different step size. Because instead of just using the raw gradient, you're using the running average gradient. And so you're not actually performing gradient descent, you're performing running average gradient descent, which is a different thing. And that hopefully cancels out the bad oscillations in directions of divergence. We'll stop here and we'll pick up from here in the next class. Thank you. There was a poll. I will leave this on the slides.